Welcome to The Explainer. Today, we're jumping right into a rigorous but totally accessible university-level masterclass on machine learning. Whether you're aiming to actually build these systems yourself, or you just want to decode the intelligence behind the tech that's literally shaping our modern world, you absolutely need a solid mental map of how this works from the ground up. I am so thrilled to be your guide as we tackle the core statistical principles of this fascinating field. So let's get right to it.
Here's a quick look at our syllabus. We're going to journey all the way from the practical basics of going beyond explicit programming through the machine learning pipeline, core learning paradigms, classification and generalization, and finally, we'll hit the mathematical core, statistical parameter estimation.
Okay, let's dive into this. Section 1. Beyond explicit programming, shifting the paradigm. So, what exactly is machine learning? To put it formally, it's a branch of artificial intelligence that gives computers the ability to learn patterns from data and make decisions without explicit programming. Instead of just blindly following a rigid set of instructions typed out by a human, the computer becomes this incredible engine of statistical pattern recognition. It sifts through massive amounts of information, finds all the hidden relationships, and basically figures out the rules entirely on its own.
Think about a spam filter in your email. In traditional programming, a human developer literally has to write out exact rules, like if the email contains the phrase free money, mark it as spam. But spammers get smart, right? They change their wording. With machine learning, we aren't writing those rules. Instead, we feed the computer thousands of examples of spam emails and thousands of normal, safe emails. The model learns all the subtle, complex patterns independently and then uses that learned experience to accurately predict if a brand new, unseen email is spam. It's a total game changer.
Moving right along to Section 2, the machine learning pipeline, step by step.
Every single successful machine learning project follows these 4 sequential steps. First, data collection, gathering the raw information. Second, data preparation, systematically cleaning out errors and missing values. Third, training the model, feeding that data to an algorithm so it can actually find the patterns. And fourth, testing and evaluation, verifying the model's accuracy on totally new data. Imagine you're trying to predict student exam marks. You'd collect historical data on attendance and study hours, clean it all up, train the algorithm to see that, hey, more study hours generally correlate with better marks, and then you test it by having it predict the marks of current students it has never seen before.
Now, what's really interesting about this workflow is how the raw input data, let's say images of various animals, actually moves through the training phase. The algorithm acts like a set of gears grinding through the data, mathematically processing the pixels and shapes. By the time it outputs a prediction, it has successfully sorted that completely unseen data into categories like elephants, camels, and cows.
Section 3. Core learning paradigms, how machines learn. Because we have so many different types of data, we need different frameworks for the machine to learn from them.
And why does mastering these different frameworks matter? Well, we use different learning methods to power disease prediction in healthcare, personalized tutoring in education, real-time fraud detection in finance, product recommendations in business, and the incredibly complex environmental processing needed for self-driving cars. The stakes here are massively high, which means the underlying mathematical frameworks have to be remarkably precise.
The first major paradigm is supervised learning. This is a highly structured environment where the model is fed labeled data. So it's explicitly told that a specific shape is a hexagon and another one is a triangle. The machine learns by example, very much like a student learning under the direct supervision of a teacher. The whole goal is just to map the input data to the known output data so it can accurately label test data later on.
Now, contrast that with unsupervised learning. Here, the machine is essentially thrown into the deep end. The input data is entirely unlabeled, just a random assortment of, say, cat and dog photos with 0 tags telling the machine what they are. The algorithm has to act autonomously to interpret the data, using techniques like feature extraction and dimensionality reduction to find hidden commonalities and automatically cluster the photos into distinct groups on its own.
Let's move to Section 4 and see how this builds into classification and generalization, making useful models.
When we want our supervised learning models to actually categorize things, we use classification. This is where the model learns from labeled training data and then predicts the class of new, unseen data. And I want to really emphasize unseen data here. That is the true test of classification. Remember our spam filter from earlier? That is a classic binary classification problem, spam or not spam. Or, going back to our student example, pass or fair.
But you might be wondering, how does an algorithm actually make a decision on data it has literally never seen before?
It relies on a super important university-level concept called inductive bias. Basically, an algorithm must inherently make assumptions. Think of this as the algorithm applying Occam's razor. It naturally prefers the simplest possible hypothesis or model that fits the data. Without this built-in bias towards simplicity, learning just wouldn't be possible, because the algorithm wouldn't know how to choose between infinite possible, overly complex explanations.
So, the crucial point is that a model is only valuable if it can generalize. Good generalization means the model has learned the true underlying patterns and is highly accurate when faced with the real world. The absolute enemy of generalization is something called overfitting. Overfitting happens when a model essentially memorizes the training data perfectly, including all the random noise and weird anomalies, but then completely fails when tested on new data. It's exactly like a student memorizing the exact answers to a practice test without actually understanding the underlying subject matter. They're going to fail the final exam.
Section 5. Statistical Parameter Estimation, the Mathematical Core.
All right, prepare yourself. We are bridging the gap from practical models into pure statistical probability. We're going to start with maximum likelihood estimation, or MLE. MLE is a statistical method that tries to find the most accurate parameters for a model by choosing the values that make the specific training data we've observed the most mathematically likely to occur. So if you flip a coin 10 times and get 7 heads, MLE simply assumes the coin is biased to land on heads 70% of the time. It is looking strictly and exclusively at the data right in front of it.
But there is a more sophisticated alternative, maximum a posteriori, or MAP for short. MAP doesn't just look at the observed data. It mathematically combines the observed data with the Bayesian prior. And Bayesian prior is just the formal academic term for our initial knowledge or historical context about what those parameters probably should be.
And this brilliantly illustrates the exact difference. MLE essentially operates in a vacuum, using only the observed data. MAP takes a much broader view, incorporating that prior historical context to weight its decisions. This makes MAP incredibly robust, especially when you already have some strong domain expertise about the problem you're trying to solve mathematically.
Math-wise, this is super elegant. MLE is attempting to maximize the likelihood of the data given the parameters. MAP, on the other hand, is attempting to maximize the posterior probability. It isn't just looking at the present, it's actively updating reality, calculating the new probability of the parameters after factoring in both the fresh evidence and the established prior assumptions.
Both of these statistical estimations sit under the grand umbrella of Bayesian learning. Rooted in Bayes' theorem, this is a seriously powerful approach that uses probability to represent our uncertainty about the world. It provides a strict, elegant mathematical framework for updating our beliefs the exact moment new data becomes available.
Which leaves us with this profound question at the very heart of Bayes' theorem, and honestly, at the heart of machine learning itself. Given new evidence, how should we update our belief? Machine learning algorithms are answering this question millions of times a second. I challenge you to think about how you process new data in your own life. Thank you so much for joining me for this masterclass on the Explainer. Keep analyzing, and I'll catch you next time.